I'm glad you found your way here tonight, whether you're settling into bed, leaning back in a chair, or simply giving yourself a moment away from the rush of the day. There's no hurry here, no countdown, no need to keep track of anything at all. Just a gentle journey through ideas that are big enough to make everyday worries feel a little smaller. Tonight we're drifting toward a question that starts with something simple and grows into something vast. A question about size, distance, and what it really means to be large in a universe that already feels impossibly wide. Somewhere out there, far beyond the familiar dots of stars we see from our windows or city streets, are worlds that stretch the limits of what we call a planet. Some of them are so big that even our own giant neighbours like Jupiter begin to seem modest by comparison. So, instead of rushing to an answer, let's ease into the idea together. Let's wander through what it means to search for the largest planet ever discovered, and why that search feels a little like standing at the edge of the ocean and wondering where the water truly ends. Before we go any further, I'd love to know something simple and human. Where are you listening from tonight? Are you tucked away in a quiet bedroom, on a late train, or perhaps under a blanket with a soft glow from a screen nearby? And what time is it for you right now, in your small and personal corner of this very large universe? It's always a comforting thought that while we're talking about distant worlds and enormous planets, we're also sharing this gentle moment across many different places, all connected by the same slow turning of the Earth. If this calm little expedition turns out to be a pleasant part of your evening, if it helps you relax or sparks a bit of quiet curiosity, you're always welcome to show a little support by liking the video or subscribing. It helps this space reach other listeners who might be looking for the same kind of peaceful pause. There's no pressure, of course. Just consider it a friendly wave across the cosmic distance. Now, let's begin with something familiar. Close your eyes for a moment if you'd like, and picture our own solar system. The warm glow of the sun at the centre, the rocky inner planets circling close by, and then, farther out, the giants. Jupiter, with its wide stripes and swirling storms. Saturn, with its thin, elegant rings. These worlds already feel enormous compared to Earth. If you could place Earth next to Jupiter, it would look like a small marble beside a beach ball. Jupiter is so large that more than 1,000 Earths could fit inside it. That alone sounds impressive enough to win a cosmic size contest. And yet, in the wider universe, Jupiter turns out to be more of a starting point than a final answer. The night sky we see is only a tiny slice of what's really out there. For most of human history, every star we looked at was just that, a point of light, distant and unreachable. It wasn't until fairly recently on the scale of history that we realised many of those stars are not alone. They have planets of their own, circling them quietly, just as our planets circle the sun. These distant worlds are called exoplanets, and discovering them has become one of the most exciting parts of modern astronomy. The first confirmed discovery of an exoplanet around a sun-like star happened in 1995. That might sound like a long time ago, but in scientific terms it's very recent. Since then, astronomers have found thousands more. Some are small and rocky, like Earth. Some are frozen and distant from their stars. Others are so close to their suns that their atmospheres are being blown away by heat and radiation. And then there are the giants, the ones that make Jupiter look like it didn't quite live up to its full potential. But here's where things get interesting. When we talk about the largest planet, what do we actually mean? Are we talking about the one with the biggest mass, the most material packed into it, or the one with the largest diameter, the widest stretch from one side to the other? Because in space, those two things don't always line up the way you might expect. Imagine two balloons. One is filled tightly with air, firm and heavy. The other is much larger, but only lightly filled, puffy and soft. The second one takes up more space, but the first one might actually weigh more. Planets can behave in a similar way. Some of the largest looking planets, the ones that stretch out wide in space, aren't necessarily the most massive. They're often made mostly of gas, and their material can be spread out in a kind of swollen, expanded state. This means the search for the largest planet becomes a bit like asking whether you care more about height or weight when deciding who is the biggest person in a room. Astronomers usually focus on size in terms of radius or diameter, how wide the planet is, because that's something they can often measure more directly when a planet passes in front of its star and blocks a bit of the light. That method, called the transit method, has become one of the main ways we discover and study exoplanets. When a planet moves across the face of its star, from our point of view, the star's brightness dips slightly. By carefully measuring how much light is blocked and for how long, scientists can estimate how big the planet is. It's a delicate measurement, often involving changes in brightness smaller than 1%, but with modern telescopes and patient observation, it works remarkably well. As this technique improved, astronomers began to notice something strange. Some of the giant planets they were finding were far larger than anything in our own solar system. These weren't just Jupiter-sized worlds. They were Jupiter turned up to 11. Many of these enormous planets orbit extremely close to their stars, much closer than Mercury is to the Sun. Because of that, they are incredibly hot, with temperatures that can reach thousands of degrees. The heat causes their atmospheres to expand, making them puff up like overheated balloons. These planets are often called hot Jupiters, and they are some of the largest looking worlds ever observed. One of the early surprises was a planet called HD 209458b. It was one of the first exoplanets observed passing in front of its star, and it turned out to be larger than Jupiter, even though it had a similar mass. That alone was enough to make scientists rethink how giant planets behave under extreme conditions. As more data came in, the list of oversized planets grew. Some had diameters nearly twice that of Jupiter. To put that into perspective, if you placed one of these planets where Jupiter is in our solar system, it would stretch so wide that it would start to encroach on the orbits of other planets. It would dominate the space around it in a way that feels almost theatrical. But even that wasn't the end of the story. One of the current record holders for sheer size is a planet known as WASP 17b. This world has a radius nearly 2 times that of Jupiter, making it one of the largest planets ever discovered by diameter, and yet its mass is much lower than Jupiter's. It's a giant but a very light one, at least by planetary standards. Its atmosphere is so expanded that it has been described as one of the puffiest planets known. WASP 17b orbits its star at a close distance, completing a full trip around it in just a few days. The intense heat from the star causes its outer layers to swell, creating a planet that looks enormous when measured by size alone. It's a world that seems to blur the line between a planet and something more like a drifting cloud held together by gravity. Then there's HAT P67b, another planet that challenges our sense of scale. This one is even less dense, with a size that makes it one of the most inflated planets ever observed. If you could somehow stand on a solid surface inside it, which is very unlikely since it's mostly gas, you'd find that the gravity feels surprisingly gentle for such a large world. It's a strange thought, that a planet can be so big and yet so light, relatively speaking. But here's another twist. There is a limit to how large a planet can get before it stops being a planet at all. As a giant planet gathers more and more material, especially hydrogen and helium, its gravity increases. At a certain point, the pressure and temperature in its core become so intense that it can start to fuse hydrogen, even if only briefly or weakly. When that happens, the object crosses a line and becomes something else, often called a brown dwarf. Brown dwarfs are sometimes described as failed stars, not quite massive enough to shine like true stars, but too massive to fit comfortably into the category of planets. So when astronomers search for the largest planet, they're also carefully watching this boundary. They're looking for worlds that push right up against the edge of becoming something more, without quite crossing over. This makes the title of largest planet ever discovered a moving target. As telescopes get better and surveys become more detailed, new candidates appear. Some are enormous, but turn out to be too massive and get reclassified as brown dwarfs. Others stay within the planetary range and claim a spot near the top of the size list. What's especially interesting is how these discoveries change the way we think about our own place in the universe. For a long time, our solar system felt like a kind of template. Rocky planets near the sun, gas giants farther out, everything in neat, predictable orbits. But the giant planets found around other stars often break these patterns. They're close to their stars, tilted at odd angles, or moving in ways that don't quite match what we see at home. The universe, it turns out, is much more creative with its planets than we once imagined. As you sit here, listening to this, it's worth pausing to consider how strange and wonderful it is that we can even have this conversation. That light from a distant star can travel across space for hundreds or thousands of years, reach a telescope on Earth, and be turned into a tiny dip on a graph that tells us a planet exists. And from that small signal, we can begin to picture a world so large that it makes our biggest planetary neighbour seem like a warm-up act. There's something quietly humbling about that. Not in a dramatic, overwhelming way, but in a gentle sense of perspective. The room you're in, the building, the city, the planet beneath your feet, all of it exists in a universe where largest can mean something far beyond what our everyday language was designed to handle. And yet, here we are, comfortably human, thinking about it anyway. There's something about the word big that feels simple on the surface, and yet quietly complicated the longer you sit with it. In everyday life, big usually means obvious. A tall building, a wide river, a large dog that takes up most of the couch. We don't need special instruments or careful definitions to agree on what counts as bigger than something else. But once you lift that idea out of kitchens and city streets and place it into the universe, the meaning starts to stretch in unexpected ways. Out there, beyond the thin shell of air around Earth, size isn't just a matter of comparison. It becomes a clue, a hint, a kind of fingerprint left behind by the way a world formed, moved, and changed over time. So when astronomers talk about the largest planets ever discovered, they aren't only making a list for the sake of curiosity, they're trying to understand what those enormous worlds can tell us about how the universe builds things in the first place. Let's ease into this with something familiar. Think about the planets you learned about in school. Mercury, Venus, Earth, Mars, then the giants farther out, Jupiter, Saturn, Uranus, Neptune. Even in that small lineup, size already tells a story. The inner planets are small, rocky, dense. The outer ones are huge, made mostly of gas and ice, wrapped in thick atmospheres. That pattern isn't random. It's tied to how the solar system formed from a disk of dust and gas swirling around the young sun billions of years ago. Close to the sun, it was too hot for light gases like hydrogen and helium to stick around. They were pushed away by heat and solar wind. Only heavier materials like rock and metal could clump together and form planets. Farther out, where things were cooler, those light gases could settle and gather, allowing giant planets to grow quickly and become massive, puffy worlds. So even in our own cosmic backyard, big already points to temperature, distance, and timing. Jupiter didn't just happen to be large. It became large because of where it formed and what was available to it at the right moment in the solar system's early life. Now, take that idea and expand it to the entire galaxy, and beyond that, to the countless galaxies scattered across the observable universe. Each star system is its own experiment. Different sizes of stars, different amounts of material, different environments, different histories. The planets that form around them reflect all of those factors. When astronomers find a planet that's far bigger than anything we see at home, it's like finding a sentence in a book that doesn't quite follow the grammar you thought you understood. It makes you stop and ask what rules you might be missing. One of the first reasons size matters is gravity. The more massive a planet is, the stronger its gravitational pull. That pull shapes everything around it. It influences the orbits of nearby planets. It can capture moons, dust, and even comets. In some systems, a giant planet acts like a cosmic bouncer, flinging smaller objects away or redirecting them into safer paths. In others, it can send them hurtling inward toward the star. There's a growing body of research suggesting that Jupiter played a role in shaping the history of life on Earth, not by being gentle, but by being large. Its gravity likely helped reduce the number of dangerous impacts Earth experienced over long periods of time by pulling in or deflecting comets and asteroids. It didn't make Earth completely safe, as the dinosaurs can testify, but it may have made the environment more stable than it otherwise would have been. So when scientists find planets even larger than Jupiter, they start wondering what role those giants play in their own systems. Do they protect smaller, potentially habitable worlds? Or do they make things more chaotic by disturbing orbits and sending debris flying in all directions? That question alone is enough to make bigger than big feel like more than a fun fact. It becomes part of the search for places where life might exist. Another layer to this is how planets grow in the first place. There are two main ideas about how giant planets form. One is called core accretion. In this model, a solid core forms first from rock and ice, and once it gets big enough, it starts pulling in gas from the surrounding disk. Over time, that gas builds up into a massive atmosphere, creating a gas giant. The other idea is called disk instability. Here, instead of slowly building up from a core, parts of the disk of gas and dust around a young star collapse directly under their own gravity, forming a giant planet very quickly. Both processes can make large planets, but they tend to produce worlds with different properties. A planet that formed through core accretion might have a heavier core and a more layered structure. One that formed through disk instability might be more evenly mixed, more like a giant ball of gas with less of a solid centre. So when astronomers measure the size, mass and composition of a very large planet, they're not just filling in a catalogue. They're trying to work backward. They're asking how this world came to be and what that says about the environment it formed in. Size also affects what a planet looks like over time. A very large planet can hold onto its atmosphere more easily. Gravity makes it harder for gas to escape into space. That means giant planets can keep thick, extended atmospheres for billions of years, even if they're close to their stars and exposed to intense radiation. But there's a balance here. If a planet gets too close to its star, the heat can cause its atmosphere to expand and slowly leak away, even if the planet is massive. This creates a strange situation where a planet can look very large, because its atmosphere is swollen, but at the same time it's actually losing material into space. Some of the largest looking planets discovered so far are in this category. They're not just big, they're actively changing, shedding parts of themselves into the surrounding space like slow, invisible winds. That process can leave behind a trail of gas that stretches for thousands or even millions of kilometres. In that sense, bigger than big isn't always a stable state. It can be a phase in a planet's life, a moment in time when it's at its most inflated before it gradually shrinks or transforms. There's also the question of how size relates to temperature. Large planets, especially those close to their stars, can be incredibly hot. Some of them have daytime temperatures that rival or exceed those of small stars. Their atmospheres can glow, not from nuclear fusion, but from sheer heat. That creates environments unlike anything we see in our solar system. Instead of clouds made of water or ammonia, some of these worlds may have clouds made of vaporized metals or glass-like particles. Rain on such a planet wouldn't be water falling gently from the sky. It might be molten droplets of iron or silicates, falling through an atmosphere that feels more like a furnace than a sky. When scientists talk about these planets, their size becomes part of a much bigger picture. It's not just about how wide they are, it's about what kinds of physical and chemical processes can happen in a place with that much mass, that much gravity and that much energy. Another reason size matters is how it affects our ability to detect and study these distant worlds. Larger planets are easier to find. When a big planet passes in front of a star, it blocks more light, creating a more noticeable dip in brightness. When it tugs on a star through gravity, it causes a larger wobble that's easier to measure. This means that for a long time, our view of the universe's planets was biased toward the big ones. We found the giants first because they announced themselves more clearly. Smaller, Earth-like worlds were harder to detect and took more sensitive instruments and longer observation times to uncover. So when we talk about the largest planets ever discovered, we're also talking about the limits of our technology and the path our discoveries have taken. The giants were our first teachers in the study of exoplanets. They showed us that planets could exist in places and forms we never expected. Over time, as our tools improve, we've started to fill in the smaller end of the scale, but the big ones still hold a special place because they often sit at the extremes. They push against the boundaries of what we call a planet, what we call a star, and what we think is possible in between. There's a subtle philosophical angle here too. Humans have always been drawn to extremes. The tallest mountain, the deepest ocean, the hottest place on Earth. The largest planet in the universe fits neatly into that pattern. It's a way of mapping the edges of reality, of finding the points where our familiar categories start to blur. And those blurred lines are often where the most interesting questions live. For example, consider the boundary between a giant planet and a brown dwarf. Brown dwarfs are objects that are more massive than planets, but not massive enough to sustain long-term hydrogen fusion like true stars. They sit in a kind of middle ground. They can glow faintly from the heat of their formation and from brief periods of fusion of heavier forms of hydrogen, but they never fully ignite like stars do. The difference between a very large planet and a very small brown dwarf can be subtle. It's not always obvious just by looking at size or even mass. Astronomers often have to consider how the object formed to decide which category it belongs in. Did it form in a disk around a star like a planet, or did it collapse directly from a cloud of gas like a star? So when a planet gets bigger than big, it starts to challenge not just our measurements, but our definitions. It forces us to ask what a planet really is. There's also a cultural side to this. The idea that there might be a largest planet ever taps into a long tradition of looking up and wondering how far things go. Is there a biggest star, a farthest galaxy, a most massive black hole? Each of those questions reflects a desire to understand the scale of the universe and our place within it, and every time we think we've found an answer, the universe tends to respond with something even larger, farther, or more extreme. From a more practical perspective, studying very large planets can help refine our models of physics. The conditions inside a giant planet are extreme. Pressures can be millions of times greater than what we experience on Earth. Temperatures can reach thousands of degrees. Materials behave in ways that can't be easily replicated in laboratories. By observing how these planets behave, how they interact with their stars, how their atmospheres move and change, scientists can test theories about how matter and energy work under conditions that push the limits of what we understand. In that way, these distant giants become natural laboratories. They're places where the universe is running experiments we could never set up ourselves. It's also worth noting that size doesn't always mean dominance in a simple, dramatic way. A very large planet can be surprisingly delicate in some respects. Its extended atmosphere can be sensitive to changes in the star's activity. A burst of radiation from a stellar flare can heat the upper layers and increase the rate at which gas escapes into space. Over long periods of time, this can significantly alter the planet's appearance and even its classification. A world that starts as a swollen, oversized giant might slowly shrink as it loses atmosphere, eventually becoming something smaller and denser. So big can be a temporary state, a snapshot in a long, slow process of change that unfolds over millions or billions of years. There's something quietly comforting in that idea. Even the largest planets in the universe are not fixed monuments. They grow, change and evolve, just like everything else. As you let these thoughts drift through your mind, you might notice how the idea of size begins to feel less like a competition and more like a story. Each giant planet is a chapter in the broader narrative of how stars and worlds come into being, how they interact, and how they transform over time. The universe isn't just filled with big things for the sake of being impressive. Those big things are there because of specific conditions, specific histories, and specific chains of events that played out in clouds of gas and dust long before any telescope was pointed in their direction. So when we ask why bigger than big matters, the answer isn't just about finding the winner of a cosmic contest. It's about using these enormous worlds as signposts. They point back to the environments they formed in. They hint at the forces that shaped them. They help us test our ideas about what planets can be and how far those ideas can stretch before they need to be rewritten. If size can be measured in different ways, if mass and diameter don't always agree, and if the line between planet and something else can blur, then what exactly are we counting when we talk about the largest planet? When we use the word largest in everyday life, it usually feels straightforward. The largest slice of cake, the largest suitcase at the airport, the largest building on the street. We look, we compare, and the answer presents itself without much debate. But once that word is carried out into space, into the quiet, distant realm of planets and stars, it begins to behave very differently. It becomes less of a label and more of a conversation. A question that opens into several other questions, each one gently pulling us deeper into how we understand the universe. So let's slow down and sit with it for a moment. When we ask about the largest planet ever discovered, what are we actually asking? Are we talking about the one that weighs the most, the one that takes up the most space, the one that has the strongest pull on its surroundings, or perhaps the one that simply looks the biggest from far away, stretched out under the light of its star? All of those are reasonable interpretations, and in astronomy, they don't always point to the same world. To see why, it helps to think about how planets are built. A planet isn't a solid block like a stone or a mountain. Even the rocky ones have layers, atmospheres, and internal structures. The giant planets take this complexity and multiply it many times over. They're not just big balls sitting in space. They're dynamic systems with deep interiors, thick atmospheres, strong magnetic fields, and ongoing interactions with their stars. Because of that, There are several different ways to describe how big a planet is, and each one tells a slightly different story. One of the most common measures is radius or diameter. This is the simple idea of how wide a planet is from one side to the other. When a planet passes in front of its star and blocks some of the light, astronomers can estimate how much of the star's surface is being covered. From that, they can work out the planet's size. This method has been incredibly powerful, and it's one of the main reasons we know about so many exoplanets today. But it also comes with a subtle bias. It favours planets that are large and close to their stars, because those planets create bigger, more noticeable dips in starlight. That means some of the largest planets on our lists are also the ones that happen to be easiest to see with this technique. Another important measure is mass. This tells us how much material a planet contains, how heavy it is, even if it doesn't look particularly wide. Mass is often measured by observing how much a planet tugs on its star. As a planet orbits, its gravity pulls the star slightly back and forth. This creates a small wobble in the star's motion, which can be detected by carefully studying the star's light. A planet with a lot of mass will create a bigger wobble. A lighter planet will create a smaller one. Now here's where things start to get interesting. A planet can be very massive without being very large in diameter. As planets grow more massive, their gravity compresses their material more tightly. At a certain point, adding more mass doesn't make the planet much bigger, it actually makes it denser. Jupiter is a good example of this. If you were to add more and more material to Jupiter, making it heavier and heavier, its diameter wouldn't increase very much. In fact, it might even start to shrink slightly. The extra gravity would squeeze the planet into a more compact shape. So when someone says the largest planet, they might be talking about the widest one, or they might be talking about the heaviest one, and those two titles don't always go to the same object. Then there's density, which is a combination of size and mass. Density tells us how much stuff is packed into a given volume. A planet with low density might be very large but relatively light, like a giant cloud held together by gravity. A planet with high density might be smaller but extremely heavy, packed with material under intense pressure. Some of the largest looking planets discovered so far have incredibly low densities. If you could find a bathtub big enough, and if the laws of physics were feeling especially cooperative that day, they might even float in water. That's how puffed up they are. Of course, you can't actually put a planet in a bathtub, but the comparison gives you a sense of how unusual these worlds can be. Another way to think about largest is in terms of influence. A very massive planet can dominate its surroundings, shaping the orbits of other planets, capturing moons, and controlling the flow of dust and debris in its system. In that sense, size isn't just about physical dimensions, it's about presence. How much of a mark does this planet leave on the space around it? Jupiter, again, is a good example close to home. It has dozens of moons, a powerful magnetic field, and a gravitational reach that extends far beyond its visible atmosphere. It plays a role in shaping the entire architecture of the solar system. Now imagine a planet even more massive than Jupiter. Its sphere of influence would be even larger. It might control the movements of other planets in its system in ways that are hard to predict. It could shape the disk of material around a young star, affecting what kinds of worlds form nearby. So in that sense, the largest planet might be the one that leaves the biggest gravitational footprint, not just the one that looks the widest through a telescope. There's also the question of where a planet ends. For rocky planets like Earth, the boundary is fairly clear. You have solid ground, then atmosphere, then space. For gas giants, the boundary is much fuzzier. Their atmospheres gradually thin out as you move away from the centre, fading into space rather than ending at a sharp edge. So when astronomers say a gas giant has a certain radius, they're usually choosing a specific level in the atmosphere where the pressure or opacity reaches a defined value. It's a practical choice, not a natural wall. In a sense, the planet doesn't have a single obvious surface. It's more like a deepening mist of gas that becomes thicker and denser as you move inward. That means two scientists could, in theory, use slightly different definitions and come up with slightly different sizes for the same planet. In practice, the field is settled on standard conventions, but the underlying reality remains a bit soft around the edges. Another layer of complexity comes from the fact that planets are not perfect spheres. Many of them spin, and when they spin, they tend to bulge at the equator and flatten slightly at the poles. Jupiter and Saturn both show this effect clearly. They're wider around the middle than they are from top to bottom, So when we talk about their diameter, we usually mean an average value, but even that average hides a bit of shape and motion inside it. Then there's time. A planet's size is not necessarily fixed over its entire lifetime. Young giant planets can be much larger than older ones. When a planet first forms, it can be hot and swollen, still holding on to the energy from its birth. Over time, as it radiates that heat away into space, it can cool and contract. For planets that orbit close to their stars, this natural cooling can be counteracted by constant heating from the star. That's one of the reasons some of the largest planets discovered are so close to their suns. The heat keeps their atmospheres expanded, making them look bigger than they might otherwise be. So when we measure a planet's size, we're capturing it at a particular moment in a long, slow process of change. The largest planet ever discovered might not stay that way forever, even if nothing new is found. It might gradually shrink as its atmosphere evolves. All of this means that largest is not a single, simple property. It's a bundle of related ideas, each one highlighting a different aspect of what a planet is and how it behaves. There's also a subtle distinction between what we can measure and what we can infer. For many exoplanets, we only know their size, not their mass. For others, we know their mass but not their size. Only a smaller group has both measurements, which allows scientists to calculate density and get a clearer picture of what the planet is made of. So when a list of the largest planets is published, it often depends on which planets have enough data available to be compared fairly. There may be even larger worlds out there that we simply haven't measured well enough yet to include. That brings in another layer of meaning to the word largest. It doesn't just refer to what exists, it refers to what we know exists. Our view of the universe is shaped by our tools, telescopes, instruments, observation time, and the methods we use to interpret data all play a role in what shows up in our catalogues. As those tools improve, the list of known planets changes, new giants appear, old records are broken, so the largest planet ever discovered is always a temporary title. It's a snapshot of our knowledge at a particular moment in history. There's something quietly fitting about that. The universe doesn't seem to like final answers, it offers us better and better approximations instead. Another interesting angle is how we decide what counts as a planet in the first place. We touched on this earlier, but it becomes especially important here. There is a fuzzy boundary between very large planets and very small stars, especially brown dwarfs. Brown dwarfs can be several times more massive than Jupiter. They don't shine like true stars, but they can glow faintly from internal heat and brief periods of limited fusion. Some of them even have disks of material around them, and possibly their own planets. So if we're not careful, the largest planet on a list might actually be something that belongs in a different category altogether. Astronomers often use a mass limit to draw the line. Objects above a certain mass, usually around 13 times the mass of Jupiter, are considered likely to be brown dwarfs rather than planets, because that's roughly the point where deuterium fusion can occur in their cores. But even that boundary is debated. Some scientists argue that how an object forms is more important than how massive it is. If it formed in a disk around a star like a planet, then it should be called a planet even if it's very massive. If it formed by collapsing from a cloud of gas like a star, then it should be called a brown dwarf, even if it's relatively light. This means that two objects with similar sizes and masses could be classified differently depending on their history, which we often can't observe directly. So when we talk about the largest planet, we're also stepping into a discussion about definitions, categories, and how humans draw lines in a universe that doesn't always respect them. There's a gentle irony here. We use precise numbers, careful measurements, and formal definitions to describe these distant worlds. But the reality itself is often messy, overlapping, and hard to pin down. The more closely we look, the more we find exceptions, edge cases, and objects that sit comfortably in the grey areas. In a way, that makes the question of largest more interesting, not less. It turns it from a simple ranking into an exploration of how planets work, how stars and disks give rise to different kinds of worlds, and how our own understanding evolves over time. There's also a human side to this. We like superlatives. The biggest, the fastest, the farthest. They give us a way to frame the vastness of the universe in terms that feel approachable. Saying this planet is twice the size of Jupiter is easier to picture than reciting long strings of kilometers and scientific notation. But even those comparisons are stepping stones rather than final destinations. They're ways of connecting something unimaginably distant to something we already know. As you sit with this idea, you might notice how the word largest begins to feel less like a destination and more like a doorway. It opens into questions about formation, physics, classification, and observation. It invites you to think about not just how big a planet is, but how it came to be that way, how it interacts with its surroundings, and how we came to know about it at all. How do astronomers actually discover these distant giants? How do they turn tiny changes in light and motion into pictures of worlds hundreds or thousands of light years away? If you were able to drift backward in time, not just years or centuries, but billions of years, long before Earth had oceans, before the sun had settled into its steady glow, before even the idea of planets existed, you would find yourself in a very different kind of scene. Not a sky full of stars and worlds, but something quieter and more diffuse. A wide, slow-moving cloud of gas and dust spread across space like a faint drifting mist. This is where the story of planets begins, not with solid ground or swirling storms, but with particles so small they barely seem like they could ever become anything at all. These clouds, often called stellar nurseries, are made mostly of hydrogen and helium, with a sprinkling of heavier elements, things like carbon, oxygen, silicon and iron. These heavier ingredients are the leftovers of earlier generations of stars that lived, burned, and eventually scattered their material back into space through winds or explosions. So even at the very start of planet formation, there's already a sense of history woven into the scene. The atoms that will one day become part of a planet, or a mountain, or even a living thing, have already been through at least one cosmic lifetime. At some point, something disturbs this quiet cloud. It might be a shock wave from a nearby supernova, the gravitational pull of a passing star, or simply the slow, uneven motion of the cloud itself. Whatever the cause, a region of the cloud begins to collapse under its own gravity. As it does, it spins, very gently at first, then faster as it pulls inward. The material flattens into a wide, rotating disk, with most of the mass collecting at the centre. This central region grows hotter and denser, eventually becoming a star. Around it, the disk remains, a broad, thin plain of gas and dust circling the newborn sun. This disk is where planets take shape. If you imagine looking at this disk from above, it might remind you of a vinyl record or a pancake of mist and grit, slowly turning in the dark. But unlike a record, it isn't smooth. It's full of tiny particles, grains of dust, ice crystals, and clumps of gas, all moving, colliding, and drifting past one another. At first, these particles are incredibly small, far smaller than a grain of sand. But over time, they begin to stick together. This sticking isn't always gentle. Sometimes it's more like a soft tap that causes two grains to cling. Sometimes it's a more energetic bump that shatters them apart. But on balance, more things stick than break, and slowly, almost patiently, the grains grow into pebbles. Pebbles become rocks, rocks become boulders, and boulders, given enough time and the right conditions, become something larger still. This stage of planet formation is often called accretion, which is a simple way of saying that small things come together to make bigger things. It's not a neat, orderly process. It's messy, full of collisions, near misses, and constant motion. Imagine a crowded ice rink where everyone is drifting in different directions, occasionally bumping into one another, and sometimes forming small clusters that skate together for a while. As these clusters grow, their gravity becomes stronger. That gravity begins to pull in more material from the surrounding disk. The bigger an object gets, the more efficiently it can grow. It's a kind of cosmic snowball effect. In the inner regions of the disk, close to the star, things are warm. Ice can't survive there. Only materials like rock and metal can stay solid. This leads to the formation of rocky planets, like Earth and Mars, with solid surfaces and relatively thin atmospheres. Farther out, beyond a boundary often called the frost line, it's cool enough for water, methane, and other substances to freeze into ice. This makes a huge difference. Ice is abundant and sticky. It allows growing planetary cores to gather mass much more quickly. These cores can become large enough, fast enough, to start pulling in the light gases around them, especially hydrogen and helium. This is where the story of giant planets really begins. Once a core reaches a certain size, often thought to be around 10 times the mass of Earth, its gravity becomes strong enough to hold onto a thick atmosphere. gas from the disk begins to fall in, not all at once, but steadily, layer by layer. Over time, this atmosphere can grow into something enormous, dwarfing the solid core hidden deep inside. This process, called core accretion, is one of the main ways scientists think gas giants form. It explains why these planets tend to have heavier elements in their centres and thick, lighter atmospheres around them. But this isn't the only path to a giant world. In some disks, especially very massive and cold ones, parts of the disk itself can become unstable. Instead of slowly building a core and then gathering gas, a large region of the disk can collapse directly under its own gravity, forming a giant planet in a relatively short amount of time. This is known as disk instability. Planets formed this way might not have a well-defined solid core at all. They may be more evenly mixed throughout, like a ball of gas and ice that never quite separated into distinct layers. Which of these processes dominates in the universe is still an open question. It may be that both happen, depending on the conditions in the disk and the environment around the young star. What makes this especially interesting for the question of very large planets is that disk instability might be more likely to produce truly massive worlds. If a large chunk of a disk collapses all at once, it can create a planet that starts its life already enormous, pushing close to the boundary between planet and brown dwarf. So when astronomers find a giant planet that seems unusually large or massive, they often wonder which path it took to get there. Did it grow slowly, patiently pulling in gas over millions of years, or did it form in a sudden dramatic collapse of a swirling cloud? The answers are written in things like the planet's composition, its orbit, and how it interacts with its star. As these young planets form, they don't stay neatly in place. The disk around a star isn't a calm, empty stage. It's a dynamic environment, full of gas flows, pressure waves, and interactions between growing worlds. These forces can cause planets to migrate, slowly moving inward or outward from where they originally formed. This migration is one of the reasons we find giant planets very close to their stars, even though we think they usually form farther out. A planet might begin its life in the colder outer regions of the disk, gather a thick atmosphere there, and then gradually spiral inward, ending up in a tight, fast orbit near its sun. During this journey, it can pass through regions where other planets are forming. It can disrupt their growth, scatter them into new orbits, or even fling them out of the system entirely. In that way, the birth of a giant planet can shape the entire architecture of a planetary system. So when we look at a very large planet in another star system, we're often seeing the result of a long, complex history, a story that involves not just the planet itself, but everything else that was forming around it at the same time. There's also a sense of timing involved. The disk of gas and dust around a young star doesn't last forever. Over a few million years, it gets blown away by the star's radiation or pulled into planets and other objects. If a growing planetary core doesn't reach that critical size in time, it may never become a gas giant at all. It might end up as a large rocky or icy world instead, with only a thin atmosphere. So the difference between a modest planet and a massive oversized one can come down to a kind of cosmic race. Can the core grow fast enough before the gas disappears? This helps explain why giant planets are more common around certain types of stars. Stars that are richer in heavy elements tend to have disks with more solid material. That makes it easier for cores to form and grow quickly, increasing the chances of creating large planets. In other words, even at the scale of entire solar systems, chemistry matters. As these planets continue to evolve, they don't just sit quietly in their orbits. They interact with their stars in subtle and not so subtle ways. A giant planet close to its star can be tidally locked, always showing the same face to the star, much like the moon does to Earth. This creates extreme temperature differences between its day side and night side, driving powerful winds through its atmosphere. Over time, these winds can redistribute heat, shape cloud patterns, and even affect how the planet's size changes. A constantly heated atmosphere can remain expanded, keeping the planet looking larger than it might otherwise be. Meanwhile, inside the planet, slow processes are at work. Heat from formation leaks out. Materials may separate, with heavier elements sinking toward the center and lighter ones rising. Magnetic fields can be generated by the motion of conductive materials deep within. All of these processes contribute to what the planet looks like and how it behaves billions of years after it was born. What's striking is how much of this story happens out of sight. We can't watch a planet form directly, at least not in detail. The disks are too far away, the timescale's too long. Instead, astronomers piece together this narrative by looking at many different systems at different stages of development. Some stars are very young, still surrounded by thick disks. Others are middle-aged, with a few planets already in place. Some are old, with systems that have settled into long-term stability. By comparing these snapshots, scientists build a kind of time-lapse of planetary birth and growth. This approach has revealed something important for the search for the largest planets. There doesn't seem to be a single, universal recipe. The universe is flexible. It can make small, rocky worlds and these enormous gas-dominated giants, sometimes in the same system, sometimes in very different ones. And the largest planets, the ones that stretch our definitions, often come from environments that were especially rich, especially massive, or especially dynamic. Big disks around big stars, regions where gravity and motion had a lot of material to work with. So when you hear about a planet that's nearly twice the size of Jupiter, or one that seems to sit right at the edge of being a star, you're hearing the end result of a long chain of events that began in a quiet, drifting cloud of dust and gas. There's something gently grounding about that. Even the most extreme worlds we can imagine start from the same basic ingredients. Tiny particles, simple forces, time. As you let this process settle in your mind, you might picture it not as a single moment, but as a slow, steady flow. A disk turning, particles meeting, gravity tugging, heat building and fading, orbit shifting, all of it unfolding over spans of time so long that human history would fit into a thin line at the very end. And yet, through careful observation and patient study, we found ways to read the traces of that process in the light of distant stars. If you line up all the planets we know about, both the ones close to home and the ones circling distant stars, a pattern starts to appear. It's not just a smooth scale from small to large, like pebbles becoming rocks and then boulders. Instead, planets tend to fall into families, groups defined not only by size, but by what they're made of and how they behave. And when we start talking about the biggest worlds ever found, those families become especially important, because each one comes with its own natural limits. Let's begin with the idea of a gas giant, since this is the category most people picture when they imagine a truly enormous planet. In our own solar system, Jupiter and Saturn are the classic examples. They're mostly made of hydrogen and helium, the two lightest and most abundant elements in the universe. These planets don't have solid surfaces in the way Earth does. Instead, their atmospheres gradually become denser and denser as you move downward, until the gases behave more like liquids and, deeper still, like compressed exotic forms of matter under immense pressure. Because hydrogen and helium are so light, gas giants can grow very large in diameter without needing to be incredibly heavy, at least at first. Their outer layers can stretch far out into space, creating a wide, puffy appearance. This is one of the reasons many of the largest-looking exoplanets discovered so far are gas giants. But even gas giants face a kind of ceiling. As a gas giant grows more massive, its gravity becomes stronger, and that gravity starts to squeeze the planet inward. At small to moderate sizes, adding more gas makes the planet bigger. But beyond a certain point, adding more gas mostly makes it denser instead. You can think of it like stacking soft pillows. At first, adding more pillows makes the stack taller, but if you keep piling them on, the weight starts to compress the ones underneath. Eventually, the stack doesn't get much taller at all. It just gets more tightly packed. In planetary terms, this means that there's a size range where gas giants can keep expanding, but once they reach a certain mass, their radius stops increasing significantly. In fact, very massive gas giants can be about the same size as Jupiter, or even slightly smaller, despite having several times Jupiter's mass. This is one of the reasons Jupiter holds a special place in planetary science. It sits near the peak of the size curve. There are planets heavier than Jupiter, but there are very few that are significantly wider. So when astronomers find a planet that looks much larger than Jupiter, they often suspect something unusual is going on. It may not be more massive, it may simply be hotter, more inflated, or both. Heat plays a powerful role in shaping a gas giant's size. When a planet is close to its star, the intense radiation can warm its atmosphere, causing the gases to expand. This creates what are sometimes called inflated or puffed up planets. They look enormous, but their material is spread out, making them low in density. These are the kinds of worlds that often show up on lists of the largest planets by radius. They can be nearly twice as wide as Jupiter, even if they're only a fraction of Jupiter's mass. Now let's shift to the other main family of giant planets, the ice giants. In our solar system, Uranus and Neptune represent this group. They're still large compared to Earth, but they're smaller and denser than Jupiter and Saturn. Their composition includes more heavy elements, such as water, ammonia and methane, mixed with hydrogen and helium. The term ice here doesn't mean these planets are frozen solid in the everyday sense. It refers to substances that would be ices under the cold conditions of the outer solar system, even though deep inside these planets, those materials are under such high pressure and temperature that they exist in exotic fluid-like states. Because ice giants contain more heavy material relative to light gas, they tend to be smaller in diameter for a given mass. Their gravity compresses them more effectively, leading to a more compact structure. This means that ice giants are less likely to become record holders for sheer size. Even if you added more material to them, they would tend to get denser rather than much wider. In exoplanet surveys, scientists have found many worlds that fall somewhere between the classic gas giants and ice giants. These are often called sub-Neptunes or super-Neptunes, depending on their size and mass. They can have thick atmospheres, but also a substantial amount of heavier material inside. These intermediate planets add another layer of complexity to the idea of size limits. They show that there isn't a single, clean dividing line between categories. Instead, there's a gradual transition, with planets blending into one another across a range of properties. So where exactly did the limits of size come from? Part of the answer lies in the physics of matter under pressure. As a planet grows, the pressure in its interior increases. For gas giants, this leads to hydrogen behaving in unusual ways. At very high pressures, hydrogen can become metallic, meaning it conducts electricity like a metal. This metallic hydrogen is thought to be responsible for Jupiter's powerful magnetic field. But as the pressure increases, the material becomes less compressible. It resists being squeezed further. This is what creates the plateau in the size of massive planets. Beyond a certain point, gravity can't make the planet much bigger. It can only make it heavier and denser. Another part of the limit comes from formation itself. There is only so much material available in a typical protoplanetary disk. Even in very massive disks, the amount of gas and dust is finite. A planet can't grow indefinitely unless it's in an environment with an extraordinary amount of material to draw from. And then there's the boundary between planets and stars. As a giant planet becomes more massive, its core temperature rises. At around 13 times the mass of Jupiter, conditions can become hot and dense enough for deuterium fusion to occur. Deuterium is a heavier form of hydrogen, and fusing it releases energy. Objects that can fuse deuterium are often classified as brown dwarfs rather than planets. They're not true stars because they can't sustain long-term hydrogen fusion, but they're also not quite planets anymore. This creates a kind of upper mass limit for what we usually call a planet. It's not a sharp, physical wall, but a convention based on what kinds of nuclear reactions can happen inside the object. So when we talk about the largest planet, we're usually talking about something that sits below this threshold. Something that is big, but not so big that it crosses into the realm of star-like behaviour. Within that range, size in terms of diameter tends to peak around Jupiter's scale, with some variation depending on temperature and composition. That's why so many of the largest looking planets cluster around 1 to 2 times Jupiter's radius, even if their masses vary widely. Another factor that shapes size is age. Young giant planets are often larger than older ones. They start out hot and inflated, still glowing with the heat of their formation. Over time, they cool and contract. This means that if you observe a young planetary system, you might find giants that look unusually large compared to similar planets in older systems. Given enough time, those same planets might shrink and become more compact. So a list of the largest planets is also, in a way, a list of planets caught at particular moments in their lives. There's also the role of atmosphere loss. Planets that orbit close to their stars can lose parts of their atmospheres over time due to intense radiation. This can strip away the outer layers of gas, making a planet smaller and denser. Some scientists think that certain classes of planets we see today, such as hot Neptunes or super-Earths, might be the exposed cores of what were once much larger gas giants. If that's true, then the largest planets may represent a phase that some worlds pass through, rather than a permanent state. When you put all of this together, the idea of a hard, universal size limit starts to feel less rigid and more like a set of overlapping constraints. Physics, chemistry, formation history, environment and time all play roles in shaping how big a planet can become and how big it remains. There's something quietly elegant about that. The universe doesn't hand out simple categories with fixed boundaries. It offers ranges, trends and exceptions. It lets worlds exist along a spectrum rather than in neat boxes. From a practical standpoint, this also means that when astronomers announce the discovery of an exceptionally large planet, they often follow it with a series of careful clarifications. How massive is it? How hot is it? How old is the system? How close is the planet to its star? Each of these details helps place the planet within the broader context of what's physically possible. And sometimes, those details reveal that the planet isn't quite as extreme as it first appeared. A planet that looks enormous might turn out to be very light and inflated. One that seems incredibly massive might actually be on the border of being a brown dwarf. Still, even with those caveats, these giant worlds remain fascinating. They show us what happens when the basic ingredients of the universe, gas, dust, gravity, and time, are given the right conditions to build something on a truly grand scale. There's also a broader implication here for how we think about planetary systems as a whole. The presence of a very large planet can shape the destiny of everything else around it. It can influence where smaller planets end up, whether stable orbits can exist, and how material moves through the system. In some systems, a giant planet might prevent smaller worlds from forming close to the star by sweeping up or scattering the material they would need. In others, it might migrate inward and disrupt already formed planets, changing their orbits or ejecting them into space. So the limits of size are not just about the planet itself, they're about the balance of the entire system. As you let this settle, you might picture a young star surrounded by a wide, glowing disk, with clumps forming, growing, and moving through it. Some of those clumps will become modest worlds, others will grow into giants, and a few, under the right circumstances, will push right up against the boundaries of what we're comfortable calling a planet. Those boundary-pushing worlds are often the ones that catch our attention. They're the ones that make headlines, that get described as record breakers or cosmic oddities. But beneath that surface excitement is a quieter story. A story about how nature builds things, how it balances forces, and how even the largest creations are shaped by the same basic rules as the smallest ones. When people first start thinking about giant planets, there's almost always one name that comes to mind before any other: Jupiter. It sits there in the night sky, bright enough to be seen with the naked eye, steady and calm like a quiet landmark among the shifting patterns of stars. Long before telescopes, long before anyone knew what a planet really was, humans noticed Jupiter and gave it a place in their stories, their calendars, and their sense of the heavens. So when astronomers go searching for worlds that are bigger than anything we know, Jupiter naturally becomes the reference point. It's the familiar giant, the one we measure everything else against, the yardstick for large in planetary terms. Let's take a slow, careful look at what makes Jupiter what it is, because understanding this one world makes it much easier to appreciate just how unusual some of the larger planets out there really are. Jupiter is massive in a way that's hard to translate into everyday experience. It contains more than twice the mass of all the other planets in our solar system combined. If you were to scoop up Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, and somehow press them together into a single object, Jupiter would still outweigh them. That alone gives it a kind of gravitational authority in our corner of the galaxy. Its diameter is about 11 times that of Earth. That means you could line up 11 Earths side by side across Jupiter's face, and still have room to spare. And as impressive as that is, it's the volume that really stretches the imagination. More than 1,000 Earths could fit inside Jupiter's vast interior. Yet for all that size, Jupiter is mostly made of the lightest stuff in the universe: hydrogen and helium. If you could somehow remove all of Jupiter's material and lay it out in front of you, you wouldn't see mountains of rock or oceans of water. You'd see enormous quantities of gas compressed under gravity into layers that behave in ways we don't usually encounter on Earth. The outermost part of Jupiter is its atmosphere, a thick, swirling envelope of clouds and storms. Those familiar bands you see in telescope images, the light and dark stripes running parallel to the equator, are actually powerful jet streams. They're winds that race around the planet at hundreds of kilometers per hour, circling it in alternating directions. Then there's the Great Red Spot, a storm so large that Earth could fit inside it. It's been raging for at least a few hundred years, possibly longer. While storms on Earth come and go, shaped by continents and oceans, Jupiter's storms can persist for generations, fueled by the planet's internal heat and rapid rotation. That rotation is another key feature. Jupiter spins fast. A day on Jupiter lasts just under 10 hours. Because it's so large that rapid spin gives it a noticeable bulge at the equator, it's not a perfect sphere. It's slightly squashed at the poles and wider around the middle, like a soft ball spun just a little too quickly. Beneath the visible clouds, the atmosphere becomes thicker and denser. Hydrogen gas transitions into a liquid-like state, and deeper still, under immense pressure, it becomes metallic hydrogen. This is a strange form of matter, where hydrogen, usually a simple gas, behaves like a metal and conducts electricity. It's this metallic hydrogen layer that's thought to generate Jupiter's powerful magnetic field. That magnetic field is the strongest of any planet in the solar system. It extends millions of kilometers into space, creating a vast region around Jupiter where charged particles are trapped and guided by invisible magnetic lines. Jupiter's influence doesn't stop with its atmosphere and magnetism. It has a whole family of moons, more than 90 known so far. Some of them are small, irregular chunks of rock and ice. Others are worlds in their own right. The 4 largest, known as the Galilean moons, were discovered by Galileo Galilei in 1610. Io, Europa, Ganymede, and Callisto. Each one is different, and each one has played a role in shaping how we think about what moons and planets can be. Io is the most volcanically active body in the solar system, its surface constantly reshaped by eruptions driven by gravitational tug-of-war between Jupiter and the other moons. Europa hides a vast ocean beneath a shell of ice, an ocean that might contain more water than all of Earth's oceans combined. Ganymede is the largest moon in the solar system, bigger than the planet Mercury, and it even has its own magnetic field. Callisto is heavily cratered, a kind of record of ancient impacts frozen in time. So when we talk about Jupiter, we're not just talking about a planet, we're talking about a miniature system, a collection of worlds held together by a central giant. In the broader story of planet formation, Jupiter likely played a key role in shaping the rest of the solar system. Its gravity influenced the distribution of material in the disk that surrounded the young sun. It may have limited the growth of Mars by sweeping away or redirecting material that might otherwise have gone into building a larger planet. There's also evidence that Jupiter didn't always sit exactly where it is now. Some models suggest that it migrated inward and then outward again during the early history of the solar system. If that's true, it would have had an even more dramatic effect on the orbits and formation of the other planets. So Jupiter isn't just big, it's influential. It's a kind of architect of the system it lives in. Because of all this, Jupiter became the natural benchmark for giant planets beyond our solar system. When the first exoplanets were discovered in the 1990s, many of them were described in terms of how they compared to Jupiter. A planet might be half the mass of Jupiter, or twice the size of Jupiter. The name Jupiter itself became part of the language of exoplanet science. Terms like hot Jupiter emerged to describe gas giants that are similar in mass to Jupiter, but orbit very close to their stars. These worlds challenged expectations, because in our own system, giant planets are far from the Sun. Finding them hugging their stars forced scientists to rethink how planets move and settle into their final orbits. So in a way, Jupiter is not just a benchmark, it's a starting point for surprises. It represents a kind of balance point in planetary physics. It's massive enough to dominate its surroundings, but not massive enough to become something else. Like a star or brown dwarf, it's large enough to hold a thick, deep atmosphere, but not so large that its gravity compresses it into a much smaller shape. As we talked about earlier, adding more mass to a gas giant beyond Jupiter's range doesn't make it much bigger in diameter. It mostly makes it denser. That's why Jupiter sits near the top of the size curve for planets. It's close to the maximum width that a typical gas giant can have without special circumstances. This is what makes the largest looking exoplanets so intriguing. When scientists find a planet that appears significantly wider than Jupiter, they know something unusual is happening. The planet might be extremely hot, it might be very young, its atmosphere might be in a highly inflated state, so Jupiter becomes a kind of reference anchor. It tells us what a normal giant planet looks like under more moderate conditions. It also gives us a nearby laboratory to test our theories. We can send spacecraft to Jupiter, we can fly past it, orbit it, and drop probes into its atmosphere. Missions like Galileo and Juno have given us direct measurements of its gravity field, its magnetic field, its atmospheric composition, and its internal structure. These detailed observations help scientists build models of how giant planets work, and those models can then be applied cautiously to the distant giants we can only study through light curves and spectra. Jupiter's atmosphere, for example, contains clues about the conditions in the early solar system. The relative amounts of different elements can tell us about where and how it formed. Did it form quickly? Did it gather material from a wide region of the disk? These are questions that connect Jupiter's story to the stories of giant planets everywhere. There's also a subtle psychological role that Jupiter plays. Because it's visible from Earth and easy to spot, it feels more real than most of the distant exoplanets we talk about. You can step outside on a clear night and see it for yourself. A bright point of light that you now know is a world larger than 1,000 Earths, surrounded by dozens of moons, wrapped in storms that have lasted longer than most human civilizations. That sense of connection makes it easier to grasp the idea that there could be worlds even larger, even more extreme, out there among the stars. When astronomers say a planet is 2 times the radius of Jupiter, they're not just giving a number, they're inviting you to take everything you know about Jupiter, its size, its storms, its gravity, its family of moons, and then imagine something that stretches even farther into space. It's worth pausing on that for a moment. Imagine Jupiter in your mind. Now imagine a version of it that's nearly twice as wide. The storms would be larger, the gravity at the cloud tops might feel gentler because the mass is spread out. The atmosphere would extend even farther, fading slowly into space. It would still be a gas giant, but it would feel like a different kind of presence, something more diffuse, more expansive. This comparison also highlights an important point. Jupiter is, in many ways, a stable giant. It's been around for billions of years, and it will likely remain much as it is for billions more. Some of the larger-looking exoplanets may not have that kind of long-term stability. Their inflated atmospheres could be temporary, slowly eroded by their stars, so Jupiter becomes a kind of baseline for what a long-lived giant planet looks like. Another reason Jupiter is so central to these discussions is its role in our search for life. While Jupiter itself is not a place where life as we know it could exist, its moons, especially Europa, have become prime targets for exploration. The idea that a moon of a gas giant could harbour a subsurface ocean and potentially the conditions for life has expanded the way scientists think about habitable environments. This means that giant planets can be important not just as objects of interest themselves, but as hosts for other worlds that might be more welcoming. So when we talk about very large planets in other systems, part of the question becomes whether they might also have families of moons, and whether those moons might have environments shaped by the gravity, radiation, and heat of their giant parent. That adds another layer to the meaning of big. It's not just about the planet's own size, it's about the size of the system it creates around itself. Jupiter's magnetosphere, for example, is so large that if it were visible from Earth, it would appear larger in the sky than the Moon. It's an invisible bubble of influence that extends far into space, interacting with the solar wind and shaping the environment around the planet and its moons. So when we look at a massive exoplanet, we can wonder about the invisible structures around it, the magnetic fields, the radiation belts, the regions where charged particles dance and spiral. These are all parts of what it means to be a giant in space. In that sense, Jupiter isn't just a measuring stick, it's a model, a kind of template for what a large planet can be, what it can do, and how it can shape its surroundings. As you let this familiar giant settle in your thoughts, it becomes easier to see why astronomers often start their comparisons here. Jupiter is the known reference, the giant we can study up close, the one that anchors our imagination when we look at the data from distant stars. There comes a point, when you spend enough time thinking about planets and gravity and gas and the quiet rules that seem to guide how the universe builds things, that certain expectations settle into place. you start to feel like you understand the general shape of what's possible. You learn that rocky worlds stay relatively small, that gas giants grow large but not endlessly large, that stars are the ones that truly dominate in size and mass, and somewhere in between, there's a comfortable boundary where planets are supposed to stop and something else is supposed to begin. So when astronomers began to find planets that appeared larger than Jupiter by a wide margin, it felt, at first, a little like someone had quietly moved that boundary without telling anyone. Because according to many of the simple models, Jupiter is already close to the practical upper limit for how wide a planet should be. Add more material, and gravity should squeeze it down, not let it puff out. Make it heavier, and it should get denser, not broader. In that neat, tidy picture, a planet that looks much bigger than Jupiter shouldn't really exist. And yet, there they were. Not just one or two, but a growing list of worlds that seemed to stretch beyond the comfortable expectations. Planets with radii 1.5 times that of Jupiter. Some approaching nearly twice its size. Worlds that, if placed in our solar system, would loom so large they would feel almost out of place, like something that wandered in from a different category entirely. At first, the natural reaction was to question the measurements. Maybe the stars were larger than expected. Maybe the dips in light were being misinterpreted. Maybe these objects weren't planets at all, but something closer to brown dwarfs or small stars. But as more data came in, from different telescopes and different methods, the picture held. These worlds were real. They were planets by most accepted definitions, and they were, in terms of sheer width, bigger than Jupiter. So the question shifted. Instead of asking whether they existed, scientists began asking how. One of the first clues came from looking at where these planets were located. Many of the largest looking planets orbit extremely close to their stars. Not at the comfortable distances we associate with Jupiter or Saturn, but in tight, fast orbits that take just a few days to complete. In these environments, the star is not a distant source of gentle warmth. It's a blazing presence in the sky, filling much of the planet's horizon, pouring energy into its atmosphere day after day, year after year. That energy does something important. It heats the planet's outer layers, and when gas heats up, it expands. This might sound simple, but on a planetary scale, the effect can be dramatic. The atmosphere of a gas giant can swell outward, becoming thicker and more extended. The planet doesn't gain much mass in this process, but it gains size, in the sense that the region where the atmosphere is dense enough to block starlight moves farther out into space. So when astronomers measure the radius of such a planet, they're often measuring the outer edge of a very expanded, very heated atmosphere. The solid core, if there is one, might not be much bigger than Jupiter's. The extra width comes from a kind of atmospheric halo, a thick envelope of gas that's been puffed up by constant heat. This idea, known as planetary inflation, has become one of the leading explanations for why some planets look so much larger than Jupiter. But even that explanation has limits. If heat alone were responsible, then all close-in gas giants should be similarly inflated. But in reality, some are, and some aren't. Two planets at similar distances from their stars with similar masses can have very different sizes. This suggests that other factors are at play. One possibility is internal heat. Some planets may have ongoing sources of energy inside them, such as slow contraction, tidal heating from gravitational interactions with their star or other planets, or even residual heat from their formation. This internal energy can add to the heating from the star, keeping the atmosphere expanded for longer periods of time. Tidal heating in particular can be significant. If a planet's orbit is slightly stretched into an oval shape rather than a perfect circle, the gravitational pull from the star changes as the planet moves closer and farther away. This changing pull can flex the planet, generating heat inside, much like bending a piece of metal back and forth can make it warm. Another factor is composition. The exact mix of elements in a planet's atmosphere and interior can affect how easily it absorbs and retains heat. Some gases are better at trapping energy than others. A planet with an atmosphere rich in certain compounds might stay puffed up longer than a planet with a different mix, even if they're otherwise similar. Then there's age. Younger planets tend to be larger. They're still hot from their formation, and haven't yet had time to cool and contract. If you observe a young system, you might catch a giant planet in a naturally inflated state, before it settles down into a more compact form. So when a planet looks too big, it might not be breaking the rules. It might simply be caught at a moment when all the conditions line up to make it appear larger than it will be in the long run. Still, some of these worlds push the idea of inflation to its limits. Even with heat, internal energy, and favourable composition, their sizes can be hard to explain fully. This has led scientists to explore more complex models, ideas involving atmospheric circulation, where strong winds transport heat deep into the planet's interior,